Yeah, I know. And like, first, like last semester, we won the Northwest t-shirt. Wait, really? Wanna be? You got the Northwest t-shirt and she also got the Northwest t-shirt. So he should
I'm definitely good at this because I'm actually really I was nice and ready to go to bed at 11:30 last night, and I woke up at 12, and I woke up at 12:30, and I woke up at 1, and I was like,
I do that because it's like when I don't get my sleep, I'm so irritated.
It's like I'm not surprised.
I always come back to the door like pretty late, and I never I'm not loud. I was so loud this morning. I was throwing things in the trash can. I slammed the door behind me. I was like,
You should talk to them.
Alright, cool. Wrap up homework 1 and move on to the next quiz 1. At least Wednesday, we'll get to that. One thing at a time, right? So last time we drew free body diagrams, convinced ourselves in part A, like, so sum of the forces is MA, so your free body diagram equals MA. And the weird thing to get used to is just MA, you're not like trying to figure out which way MA is pointing, you're just saying this is a positive acceleration. So if it's negative, it's totally fine, it's just a negative acceleration. So in part A, we convinced ourselves that A is negative mu g, which is a constant. So if acceleration is constant, then kinematic equations are our best friend, because we already have integrated solutions, we don't have to worry about double integrals and all that. So xa equals x0 plus v0t minus mu gt squared all over 2. And that was it. That's all we needed, at least for constant acceleration. Then B, I think we got through where we said m dv dt equals negative bv. So we integrated, took this, put it over here. Did some nice magic arrow to say that x of t minus that x0 is negative mv0 over b. And I was like speed running through what we did last time to see how's it going. Also, we can stop and say, like, last time you said this, but you were talking crazy. What does that mean? Because I think this is as far as we got up to. Is that right? Does it make sense? We did more work than just writing a magic arrow, but I think we did end up at that solution. It seems right, right? Like, all right, so then we reach our last equation. A equals negative k over m x. Or another way to write this is that d squared dt squared equals negative k over m times x. I like to write those d squared dt squares as like x double dot. So this is all just like or. There's 3 different ways of writing the same thing. Have you seen an equation like this before? I'm gonna let everybody kind of get into it. Well, so just think about like, what we're trying to figure out is like, what is x of t? I know if I take negative k over m times x of t, I'll end up with the acceleration, that x double dot. So how do I find, what is x of t? Like, how do I get there? Take a derivative? Or derivative of what? So then we end up with x triple dot equals negative k over m x dot. X three dots is, we can always take derivatives like that, but I don't know if it gives us something new. Leave that out for now. What do you think? Have you seen this kind of equation before? You have like an x and then second derivative, that they're equal to each other somehow. No. It's okay. It's not like it wasn't prerequisite knowledge for today. Have you seen this before? No?
Double dot.
Either double dot or dx. I wrote it in every form that I could to see. Like, I haven't seen any of those. Well, all three of those. Have you seen this before? Yeah. Well, what did you do? Right. Yeah. With that equation, have you like seen second derivative equals
Other friends are in
function?
in South.
Okay. Yeah.
What's happening? It's just like,
No, I don't think so.
Yeah, I need to
Basically the same thing. I think it's like never later.
Yeah.
okay.
She was at home.
When we didn't see her ever since like Thursday. Like your best week.
Because the algorithm
I don't know.
it's like hard to because I was gonna say there's no scenario
I do that.
They're small.
And I don't want to be communicating.
One shower, which are 6 people times
I just feel like resources like I have enough to make my own thing.
Yes, it does not. It doesn't have like a spirit.
So as far as I can tell from my in-depth survey, no one has ever seen this this equation before. Sounds right? Or maybe at least like, maybe you saw it, but you're like, I never want to see it again, so I'm gonna pretend like I never saw it. Yeah.
I know that in my high school, I would see like for the spring force, it'd be kx equal to spring force, then force divided by mass is acceleration.
Yep.
So like that, I can see like where.
Yeah. Like it's definitely, all the pieces are there. Like we've seen springs, we know position and acceleration are related through two derivatives, but it seems like no one has come up with like, how do I start with that knowledge that like springs apply force, forces create acceleration, how do I go from there to actually saying this is my position? And it sounds like that step has never, at least not stuck, it hasn't been like, this is going to be important for the rest of my life. This is the first day of the rest of my life. So welcome to the first day of the rest of your lives, of knowing what to do. I'm going to give you the speed run for this. So we're kind of taking like a semester worth of differential equations, condensing it down into about 3 minutes worth of. So if this is my equation, and I'm trying to figure out what is x of t, I can't integrate this. Like I can't just say like, let me do two integrals at the same time and end up with an answer, because it just doesn't work. There are ways where you can kind of prove to yourself what the function is with like an infinite series of polynomials. We don't need that. Like we don't need to like figure out, is this a Bessel function or something else? I'm going to say like x of t is a function that I already know. So looking at this equation, I can kind of say like, all right, if I take two derivatives, how do I end up with the same function? And one way that I can do that is like exponential functions, right? Like an e to the t, if I take two derivatives of it, I still end up with e to the t, but it's a positive, right? And even if I have like e to the lambda t, negatives. Wait, what did you say? Sign?
Trig.
Trig? Oh, nice. Yeah. All right, nice. All right, so if I try it with like exponentials, I end up with, I'm caught in a corner where I'm trying to get a negative k over m. I'm trying to solve for negative k over m, but I have a positive lambda squared. So it's not the function that I want. Technically, I could use this, but then all my constants are going to be imaginary numbers, and I'm trying to stay in the real world. It's a whole thing. Like, imaginary numbers are great, but they add a whole extra axis to all of your numbers. So it's like, oh, geez, just give me a break. So instead, with the initial values. Yeah, with the initial, so if we know the initial position, that gives us an exact value for the initial acceleration. Yeah. And it's a numerical way of doing it, of like, all right, if I know what the acceleration is at time 0, let me take one little step. I'll step forward for 1/10 of a second, and acceleration was this, which means velocity changed by this much, and then integrate again. So we could step through it numerically like that. Or we can say, let's try just like sine. We'll just try this one to start. Like sine of omega t. So what's derivative of sine of t? Sine of omega t.
so you get side to side.
Yeah, so it's like sine of omega times t,
So
yeah.
maybe omega cosine omega t.
Yeah, omega cosine omega t. And then what's the second derivative?
Negative omega squared sine omega t.
Negative omega squared sine omega t. Which is negative omega squared x of t, right? Would this work for cosine? If I say x of t is cosine, could I say that too? Yeah. So then, like if it'll work for both, then I have to assume that it has both. So if it's sine and a cosine, then we could say like, all right, let's add a cosine too. Would it work if would it work for like 10 times sine? Like if I had an extra number to say like the amplitude of the sine wave is 10 instead of 1, would it still work? What do you think? Or does it have to be like magnitude 1 sines and cosines? Alright, try it out. X of t is a sine omega t, where a is just some number. It could be anything from 0 through 300 or 2 billion. What are those two derivatives with that a and b, sine and cosine?
Yeah, they're just like something. I don't know what they are, but I'm just trying to figure out if they're in there.
How the second derivative of function be.
If they're constant. Yeah. Yeah, this one, A and B is.
Last, I think this week, I think at least like spread out. Yeah. Two just today.
I have to move, but I don't know that. Hopefully not.
It's fine, right? It's also
How does that seem right? Where we end up with, even if I have different amplitudes for sines and cosines, it'll still work. Like, it'll still solve my differential equation, or where I'm trying to figure out, like, the second derivative is always a constant times the original function. Yeah.
So are these like confirmed position velocity and acceleration equations for the spring?
Yeah, exactly. So what we're doing is kind of like making educated guess about what the answers are going to be, so I can plug them into the original problem and solve for A, B, and omega.
I have two questions. So, sorry, does the acceleration equation just come from the kx divided by time, like the force?
Oh, like where did this one come from?
Basically just like force divided by mass. Yeah, it's not that.
That one, this we got from sum of the forces equals negative kx, which is equal to ma.
Right. And then for the one that you said instead and then gave the position equation, is that because it's like circle, like it follows circular oscillation or whatever? Like the sine plus cosine?
Yeah, so sine and cosine, you can think of those as like circle, because like trig is all based on like circular stuff. So yeah, like the phase plot, like we talked a little bit about a phase plot when we were discussing position and velocity. It's going to look like some kind of ellipse or a circle like that because it's sines and cosines. But like if you're thinking about like intuitively like why sines and cosines, like they're in this equation, the only thing that happens is I either have like acceleration because the spring is stretched, or I have a lot of speed. So it's going to bounce back and forth, and the energy is never lost. So if it's going to oscillate back and forth, then it's got to have some kind of like sine and cosine components to it, where it's swinging. Goes left, comes right, goes left, comes right. If we add friction or damping or anything like that, then maybe there's another term to say like it'll decrease over time, but roughly it kind of makes sense. Like sines and cosines should work for this problem. Did that help at all? Okay, yeah. And this is usually like the nice quick way of solving differential equations. It's like you look at the original differential equation, you're like, all right, I know that's got to be sines and cosines, so let me just plug in sine and cosine and solve for the stuff that I need to. So I'm trying to solve for this, and I'm trying to solve for A and B here and there. So we're trying to solve that next. like everything in those parentheses is x of t. So x double dot is negative omega squared x of t. So if I take that, plug it into my differential equation, it's no longer an equation with two derivatives, it's just saying that this constant times my function equals known constants times my function. So what does that tell us? What do you think? What do we have now? Does that tell us anything or no? No? Okay. Do we know any, like, does the last line, does it tell you what, like, yeah, can you solve for anything? No. Too many unknowns?
You made up enough. That's so funny. It's so
It was just to get up there. I thought I did my mission like but I do get my friends out to me. They just treat this teacher, but they're probably trying to be out. I'm literally interested. So this is the teacher. So everything on that getting closer and then she like friend at orientation. The mind map like it's crazy. So
whenever I think Hannah, I think Bella.
All right.
yeah. No, I get that.
Multiply both sides by, like, or divide by negative x on both sides. Omega squared is k over m. So, like, the frequency, the natural, this is called the natural frequency. The natural frequency of a spring mass system is square root k over m. And most of the time that's the case. Like, whatever spring and mass there is, there's usually some kind of natural frequency, which is this one, square root k over m. So it's going to oscillate, and the frequency of the bouncing back and forth is the square root k over m. Cool, that's a good start. So like x of t, now I know that it's got some sine root k over m times t, cosine root k over m times t. Good. Then the only way to get like a and b, because a and b, it doesn't matter what they are, they still satisfy my differential equation. So that differential equation works for any amplitude for cosine and sine. So the way to get like individual values is like the actual initial conditions, like where did it start? Yeah.
So for like solving this problem's purposes, could we just say they're equal to 1?
If they're both equal to 1, we could try it, yeah. So let's try both equal to 1. 1 sine root k over m times t plus 1 actually, let's just try. So my initial position is 0. So if I plug in 0 into this equation, if I have 1 and 1, is this going to be equal to 0? What's sine of 0? 0. Okay, so that one works. 1 times 0, that one's 0. What is cosine of 0? Because it's root k over m times 0. Yeah.
1.
1. Okay, so this is going to be 1 times 1. So my initial condition does not match because I said 1 and 1. So something can, and here I've got values that I can change, right? Like I can change a and b to fit my initial conditions, but I can't set them unless I know what the initial conditions are. But that was a good test, because now we know that value a can be whatever I want, and value b has to be 0, because at time 0, cosine has to be 0. So instead, let's try this. So we can't do this. So a times 0 plus b times 1. So b is 0, and that's a nice start. I think our V0 is like 10 meters per second, but I'm just going to leave it as like V0. Alright, now what do we know? Take a second, plug in some zeros, so time is 0. We should have some information about A now. Put the pieces together.
Thinking that.
Yeah.
Okay.
Yeah. Yeah.
That one's like 10 meters per second. Yeah.
Like, are you talking about the whole, like when you throw something?
Yeah, okay, yeah. This T is 0, whatever frequency is. V0, I think in this case is like 10 meters per second, but in general, it could be the whole initial speed. How's that look? Plugging in the 0, B is 0, A, so the amplitude of my cosine is that initial speed, however fast I was initially moving, divided by that natural frequency. Cool. And so this whole process is like, we took that differential equation. We didn't, if you notice, like we took some derivatives, but we didn't really do any like integrals. But really what we did by taking these derivatives and plugging them back in is we took two integrals. A and B are those integration constants. Like whenever you take an integral of x is x squared over 2 plus a. Like instead of having separate constants, they're multiplied by that function. And again, this is like a speed run through differential equations. So if you do take DiffEqs next semester, or you're taking it now you can like speed through it because you know the shortcut. Just like plug in the answer and then you can get the answer. So x of t is v0 over root k over m sine root k over m times t. So we got xa, we got xb, and now we have xc. We have the solutions for all three values. And gotta grab these. I'm gonna put them all in one spot. And can I get this? Okay. Gotta bear with me as I move things around. So x c x b, and I'm just gonna delete that. Move this over. 3 answers. We can make 3 like plots of stuff. So we'll throw this one. And I'm just going to start like from a blank notebook, but you could open up the same, at least if you want to try, like this is a great chance to make this plot. If you want to like keep pushing Jupyter knowledge, like Jupyter Python, this is a great chance to like try something else with it, make a plot that compares these 3 answers. If not, Excel works, like you can plug in these values and plug in these equations and plot it in Excel, however you want to make your plot. But I like Python, so I'm going to do some Python work. So I'll start off by importing NumPy, Matplotlib, and using the style that I like. Oh, and those are okay. So x0 is 0, v0 is 10, m is 1 kilogram, mu is 0.5, b is 1 kilogram per second. Kind of a weird unit for damping, but that's how the units end up working out, so that you get newtons when you have b times velocity. So you get a kilogram meter per second squared. And then k is 4 newton per meter. Time is always our independent variable, so I can define it however I want. In this case, I want 0 to 3 seconds. So 0 to 3. If this was Excel, then I would create a column of time and just say like B2 equals B1 plus 0.01 seconds and copy it all the way down. So XA is our, oh wait, we lost our solutions. There we go. XA is our kinematic equation. X0 plus V0 times T minus mu times, I didn't define G, did I? G times T squared over 2. I like to check one thing at a time. You end up with the same thing that happened in that homework 0 Python, like friction is a constant force, which is true. Like there's nothing that changes friction as you're moving fast or slow, and your position doesn't really change friction. But if you stop moving, friction stops working. It doesn't continue pushing you backwards. So I think in the first homework, what we did was like solve for velocity, and when it's equal to 0, when it's less than 0, set everything, have it stop changing, like XA is no longer. So let's copy this so I can do a derivative. So I'm going to say anything where the velocity is less than 0, just leave it at whatever max displacement I got to. Because as I reach the max, I should come to a stop rather than coming back down. And now I've got constant acceleration, and then I stop. And then just, that's where I sit for all time. Cool. Oh. And really all I'm doing is like taking this equation and just writing it out. And just writing it as a kind of Python version of it. And that's what I did for the first part too. Over B. And I took that exponential function that we solved for on Friday, plugged it in. I can see like for the first like quarter of a second, both of them look exactly the same. Like their initial velocity is the same, and they're both slowing down roughly. It's not always the same rate, but but we're kind of seeing like what the difference between friction and damping is. So you can, yeah.
Can you show us how to open a new project on GitHub to do this out?
Oh yeah, on like NanoHub.
Yeah, this.
So in here, if you say like file, you can, in the file menu, you can say like open, and then it'll ask you like, do you want a new notebook? Let's get the menu the same to look the same. New notebook, and we can say Python 3.8 if you want to create like a blank page. Yeah.
Is it okay to just like insert these cells on the bottom of the homework page?
Yeah, definitely. So if you want to say, like we have homework 0 in our getting started, right? Is it in here? Yeah. Is this right? I feel like I'm in the wrong NanoHub. I think I went to a CompMech one. Sorry. But anyway, you could open up that the same like homework 0 that we were working on in that getting started folder and start there, since we already have that first blue plot, like the beginning of that, and then just add the other ones. Get rid of that menu. Oh, it didn't like that, huh? Here we go. And then XC is going to be that final like sine wave kind of plot, where we have V0 over square root K over M times that sine square root K over times T now I can look at springs, dampers, and friction all in one, like what the result of all three are. So with a spring, and this is kind of general result that you, as engineers, maybe you knew this was coming, but like if you add more springs to things, it's never going to slow you down. Like it does slow me down. Like there is a zero velocity at some point, but now I've got potential energy, so it's going to speed me up again. Versus like dampers and friction, that's ways where you can take away energy, where the velocity, your kinetic energy is being dissipated somehow. So we have these three different kind of mechanisms for how forces get applied to things. Cool. Let's zoom out a little bit so we can see like setup. Yeah.
I didn't know what we didn't know. Just like that just probably really hard to I guess it's not actually
Like this one, so we'll catch up. This top one, yeah.
I just think
That's the way that I like to import everything. And usually, you'll find those first two lines everywhere in people's like Python scripts because it's so common. Yep.
next year. Yeah, I just didn't know. Are there still no. Yeah,
You have to make a plot with those things in there.
I don't think of one.
You want to use Python?
It's not,
You want to use something
I'm not
else?
saying that. I will literally say like it just doesn't work out. I just think it's like I don't know. I mean like I guess it's like the environment really between each other.
So